So first I'd like to thank Biodati for inviting me. It's great to see so many familiar faces. Oh, good. And then everything should come up right. So, hi, I'm Eric Newman. I've been interested in sort of the BEL and Solventa goals for many years. There was a time when I was even working with them back in the early days. And I think at the core of it was that knowledge and graphs and data sort of connected. And they are, but I don't think we fully explored all the possibilities. So I want to give a talk that eventually is going to lead to what we're intending to do with Biodati data in the BEL format, and some other places it might be applied to. Just a little bit of background. Last year we started IDACA, and IDACA is a deep learning company. It specifically utilizes and develops technologies to integrate biological knowledge into the learning process. Why? If AI is so great, why not just do it without any knowledge, just data? And the answer is there's not enough data to do it well. So if you put knowledge into it, that's a kind of prior. What happens to the applicability of deep learning to clinical and omics data? And that's one thing I've been interested in even prior to Foundation Medicine. But I think, we need a certain set of tool sets in any platform. And that's one thing I wanted to really develop. And utilizing graph information is a very important piece for IDACA's transparent deep learning technology, which I'll talk briefly on. I have only a few slides, but I wanted to sort of make this fun, a little bit background leading up to that. So, I'm interested in talking about graphs, which include any kind of data graph or semantic graph, analytics and deep learning. So we'll touch on that. Of course, being buzzword compliant, I have to mention something about big data, which is really, we don't have it yet, but we'd like to be able to argue it's going to be useful. So give us some money now. And then data semantics, which has come around a long way. And I think there's some trends that I'd like to point out that are very useful for a lot of different platforms and analytics and deep learning, but I'll give a specific case here. And then how to bring it together, which is really what IDACA is doing currently. So let's start with some engineering. So I think underneath all of this is that there's an engineering way of looking at the phenomenon, but medicine is not really an engineering field. Well, there is bioengineering, but in medicine and clinical data, it's not yet engineering. And there's a couple good reasons it isn't yet. But nonetheless, when you look at something this complex, which is trivial compared to the human body, so every doctor has to work with something even richer than that, the real problem is if you don't codify this structure, the diagram that is trying to be a close model, an approximation to the real phenomenon, you're never going to be able to read, interpret signals or figure out how to improve a step or a process or even put in new technologies. So a lot of the things we do in engineering, I think, are probably just a few decades away to what we want to do in biology. And that's anything from CRISPR to integrating, micro technologies into humans. But we don't even understand the biology, so I think BEL has been one of the most ambitious approaches to try to build a framework that bridges mathematics and constructive engineering into the molecular genetics point of view. So try to go through these to make sure we keep on time. We talk about data sets. Probably this group is more able to imagine it's not just data tables, it's probably graphs. But the thing is, even though you are using technologies that are great at finding patterns in relational tables and databases that are currently out there, the truth is there really are graphs behind it. It's just we don't want to try to put too many kind of edges and nodes inside it. But they're there. Anyone who's ever done a query in SQL, that's a graph join. It doesn't maybe look like it on the surface, but I'll show you that it's actually 1-to-1, 100% isomorphic. And there's a lot of things that come up with data and graphs. If you're looking at mutations, which is what I spent good last couple of years doing, their mutations are not just floating around independently. They're associated with parts of genes. So if you see that pattern over and over again, you build a graph, because each of those instances is really connecting to a exemplar of EGFR or, P53 or whatever particular gene. Patients are diagnosed around same diseases or symptoms. There's a graph. And even if you look at groupings or sets of mutations, the patterns, that becomes a node. And then you have a lot of people that are similar there, and that's a graph. So the truth is, once you start to see, it's not about the representation of the data, it's how you think of it in terms of what you can do with it, mathematically or analytically. It's always graphs. It actually can go even higher, but we won't go there yet. So what do we do with analytics? I try to sort of summarize it in a way that most people are familiar. You apply these platforms, whether you like Python or R, you're doing large-scale analyses that allow you to transform data, merge, filter it, find different clustering and patterns. And in a nutshell, that's what all machine learning and analysis is. It's nothing much more than you're trying to find a topology that you can interpret on, like why is it this way with this person or these group of people, and why do these people with this pattern not respond well to a drug? We're trying to find the underlying structure. That's really the fundamentals. And deep learning shares a lot of these approaches, but it really requires a lot of data, because you're going to use that to train on an architecture, yes, but underneath it, the transformations it's coming up with are opaque. You're not even supposed to really understand it. It's in a sense magic, but it's interesting magic because it really finds subtleties in complex things like micrographs very well. In fact, that's been shown in the last couple of years. There's several companies now that are doing a better job than most pathologists. And that's actually an interesting phenomenon. So it's not just a classification, it's restructuring the data in a way that you can get more interpretations out of. So it's an extension of analytics. And you'll see I do not like to use the word AI. It's been misused. It's full of marketing hype. And if anyone tries to keep pushing on it, every time I have to talk to Siri or Alexa, it's a joke. It's like, that's not a conversation, that's mimicry. So I know they're getting a little bit better, but most of us want to buy the whole hook and sinker, in AI, and then you have these arguments with these tools because you realize they're not that smart. So deep learning is as far as I can go. And the problem currently, and it's very hard to see, there's a link to this particular point. Most of the things you do with AI, deep learning or AI, it's alchemy. They don't really understand an exact way why certain parameters work this way, but a little bit different data doesn't. The reason it's useful is there's somebody doing a lot of recomputing deeply to guarantee that this thing's pretty stable. But actually, they don't know what they're doing. So this was Rahimi at a recent NIPS meeting, basically saying, we got to get past the alchemy. I mean, alchemy is great. That's where most of drug discovery came from, right? Early chemistry. But at some point, you got to get rules. And LeCun, of course, didn't believe that, but this is going on right now. And what we want to try to do is, okay, there's some phenomena we just want to keep an open mind and not force it. But there are other things we really have a pretty good understanding of mechanisms, or we'd like to think about this mechanism before we do any training. And the idea is to put in graph priors into the deep learning system. And what we've been discussing with Biodati is to really find the mechanism to generally take in BEL statements at the appropriate place and do deep learning on top of that. So that's sort of an interesting problem, which we'll get to in a second. But back to big data. As I said, most of us don't have it in hand, but we think it's a great thing. We want to get all the tools and technologies to pull it in. And part of it is we like to say, to get the data will allow us to predict things better. So I would say in the last couple of years, the word prediction has almost surpassed understanding. And that's troublesome, because what are you trying to really do with a prediction? Do you really know the phenomena that well? There's a lot of catchphrases going on, and I just, ahead of time, warn the audience, be very critical of these type of names coming up too often. They're going to get you stuck in a place where you're going to have trouble explaining why it's not doing what you want in your framework. In reality, you should apply things like analytics even deep learning, to do a lot of very important work before you try to predict an outcome. There's a lot there. In fact, most of the data that's out there that might have a lot of omics but doesn't have a lot of endpoints, it's really rich. Great place to go. But if you keep saying, I'm going to get this data and predict something, you're just going to be putting yourself in a hot spot soon. I've seen that happen, even at Foundation Medicine. Like, oh, when we get the data, we'll be able to do it. It wasn't working so easily. So what you can do is really focus on terms that you've probably heard that sound very dry. Data distributions and maybe something even more esoteric, manifold theory. But the reason you have to really focus on that is if you like the deep learning stuff out there, that's what's underlying all of it. So you really need to understand that before you even buy or try to program in TensorFlow or anything. It's really the data distribution, which we use the word statistics in general to talk about it, but I've come to the conclusion that we've been using these little packages to get little answers. Data distribution is a much more general phenomenon. But there's an interesting thing. The shape of the data, which is what I describe it, is really the beginning of what you do with any analysis like Bayesian graphs and Bayesian networks. And you can take a lot of immune data like that, which is this structure there, but it's sort of complex. Some is sort of nice and trendy. Some are bimodal. That information actually helps you reduce the complexity of the problem dramatically. You can go from 10,000 measurements to only maybe 5 different ranking dimensions. And 5 dimensions is a lot easier to solve than 10,000 data points or data measures. So there's a lot of good reasons to think this way, and there's a lot of very important work that's been done that way too. So and this is where I think there's a really great future for technologies like BEL. Understanding data distributions, which you can get your hands on right now, tons of it, from flow cytometry and other places, are tied, not a trivial way, but they're tied to molecular mechanisms. And they're spending billions trying to find those things with immune-related projects in pharma now. But if you want to find a single answer, an easy way to understand it, that's where you struggle. You need to have a way of thinking or a tool set allows you to juggle with 4 or maybe up to 20 different internal parameters at the same time. It's just we're not used to thinking or talking about that. But that's where, again, I think there's a lot of advantages of having prior knowledge put into a system. So one thing is, and this is, everyone faces that, there's a lot of stuff we get, even from objective measures, not just subjective, but they're confounders. And confounders will waste your time enormously, trying to find a pattern. You find a pattern, you find it's a confounded pattern. There are many, many examples. They screw up cause and effect all the time. But if you can find a way to look through that properly and improve your clinical signals, you might be able to understand a phenomenon and even suspect what are the ways to stratify a population without having to take in 10,000 samples and too much information. The idea is to do very effective work with less material, or at least what we have currently. And of course, associated with genomic effects like mutational shifts and looking at mechanisms. So to pull it together, I broke into 3 groups here to discuss. One is a little bit about transparent deep learning. What is it? And the 2 major limitations, as I've seen in this field since we were dabbling in this in the late 80s, this is actually what I had done years ago, was that you want to be able to not leave out but incorporate knowledge when available. Well, how much do you trust it? Well, let's say I know it's potentially a mechanism in some cases, but I don't know if it's really that important or if it's sufficient at all. But why not use that great deep learning technology to select and pick which pieces in some sort of intelligent way? So the idea would be that in these structures, which we've been working with several of these type of tools, whether they're variational autoencoders or generative adversarial networks, is that we can codify a structure, a constraint system, a graph logic into one of the layers and have the other layers have to interact through it. And the nice thing is that that leads to the second solution, which is another thing, is that once you have a solution, there's an opaqueness problem. How do you read out what's actually in your network? But because you've already imposed a structure inside, the way it is activated, the patterns in it, for each individual patient, it actually gives you a readout that is at the level of molecular signs or expressions. And if you're using a structure that comes from BEL, you have a way to annotate it. You could actually show which parts of these may be affected in a given individual once you apply, the same kind of molecular diagnostic platform. It's actually something we had started to do at Foundation, which was to have like a 4-tumor board. These people have a similar pattern, and this is probably what's occurring in them through the mutations. But we weren't using any other analysis besides some clustering tools. So here is sort of swapping in structured information that can be as simple as a graph that has associations and cause and effect, or can actually have, some sort of causal relations imposed in it. And one real good candidate is to use BEL for that. And here's sort of a blow-up of that. So what you have to sort of keep in mind is there is sort of the canonical stuff, and there's the stuff that's affected by individuals. And there's a set of very interesting papers that suggest how you could do these perturbations from the normal set. Again, these can be priors, but I show them here as these little orange rectangles, which are all the known possible mutations with their appropriate distribution, which can knock out different areas of the pathway. And so when you learn and train on the individuals, clinical as well as omic information, it finds and trains on the most likely candidates. A lot of this is to be done in a unsupervised or semi-supervised manner. So you don't need to have lots and lots of labeled data for this. Recent experiments I've done is to look at breast cancer transcriptomic information using only transcriptional factors and binding sites, something that we've all played with in the past with TransFac. But you can do this now with these autoencoders. And it's in this early run here, just with 5 internal nodes. So everything has to be explained by 5 parameters, and a total of 14 different transcription factors. In some cases, you can get close to 90% accuracy. In many cases, it doesn't quite fit, and that's something that's still interesting. It's an open question, but the transcriptional mapping between the factors and the binding sites in front of each gene are the only sort of graph structure we're using here. If we used other things that involve cell signaling, it might get more interesting. So this can be expanded on. And so the way we see, according to the diagram that was that Biodati provided with us, is that as the networks are being sort of built and the edges added, they can then be used to insert into a deep learning network, trained, and then, as I said, interpreted. The interpretations themselves could either be live or they can be reincorporated as nano-publishings inside the structure. And there is someone raised the question earlier about if you've got sort of this type of sort of simplified knowledge representation, you've got lots of data, like from patients and biomarkers, how do you merge the two? And there is a straight way to do that. There is a way to take the sets of things that are similar in the effects and associate them with a particular part of the pathway and mechanism. And that's, we can talk about that later. I don't want to get too much into it. But there are all various ways of then really utilizing nanopublications in a usable way. The other 2 things are really support pieces of information. I'll just go through 2 slides quickly. The key thing here is to remember the word monads. You've been using them, but you don't know it. They're in a lot of technologies, including JavaScript. But they're hidden from most programmers because, well, why make it complicated? But in analytic pipelines, they haven't been used yet. So if you try to imagine a pipeline, and we've been working with Paradigm Force IDB. In fact, we've been working with them to actually interface with deep learning. most algorithms do really great things with very simple, dumb data. So you have this sort of tension between data that can be represented in matrices and tensors, but it's pretty much just numbers, you know. And even though there might be multiple measurements, a lot of these algorithms like clustering don't have to tell me that much. I can put this together after I've normalized it in a general way. And that's more often the pattern. If you want to enlighten your analytic pipelines, it becomes a real bear. So this is something that bothered us for quite a few years, and came across a notion from somebody who works in this sort of space at MIT. And the idea is that you leave the inside the same. You wrap the outside like with a coaxial cable, and you pass minimal information through that about the metadata. And that solves a lot of different things, because that wrapper will follow what's known as a monadic algebra. You can concatenate those T's, which are the wrapper sort of metadata and other kind of important information, and they're handled independently of the internal process. So your insides are guaranteed to do the analytics they're supposed to. The outsides are guaranteed to pass along structures like metadata. So if I put in a particular structure through that, they're passed along and transformed in parallel. In fact, they can be done asynchronously. Before you even run the darn thing, you can even say what kind of output in clusters you would get and be able to even fix the GUI you want to handle that specific clinical data, though none of the A, B, C's, or D's knows anything about clinical or omics information. So it's reconstituting in a sense, but it's using this principle of monads to do that. And it basically means that if you were into graphs or RDF or JSON, you now can translate very crisply with NumPy and data frames. So I think rather than trying to format your data one way and put it through, you use this sort of post-coordinate alignment. And that's something I haven't seen anyone do in analytic pipelines, but we have the technology it's a series of classes that wrap around existing analytic tools. And just last month, we were able to wrap all of TensorFlow with the same tool. So not only can you write your pipeline with semantics that can insert BEL at the appropriate place, but you can actually rearrange those layers in a way you can't with TensorFlow alone. You don't have to write code anymore. It's automated, and itself, it can inspect itself, so you can even see how the parameters are doing. So I think it has a lot of different utility, but for instance, here's just an example of taking a pipeline that does k-means. We added this other layer, and when you do that, the display object can interrogate any additional clinical information, linked data, or it doesn't have to be, on demand, rather than having to pass the information throughout the system. So it really circumvents a lot of the complexities people have been fighting for decades, at least 30 years with data integration. I think it solves some of the problems, maybe not all. Here's an example running on Jupyter. I think a lot of people like using Jupyter these days for demonstrations. It's pretty simple and you can get a lot of stuff done. But for instance, those menu items weren't with the data. They came out of a query back to the database later on to be able to filter and select your outcomes, even though the data was in the pipeline not aware of this. And leading to another question, which it's maybe not that important a topic, but whatever happened to the semantic web, it did some things right. It focused attention on data and graphs and querying, but it really got some stuff wrong, which is why acceptance wasn't faster. And this is not just my opinion. This was one of the guys that did a lot of work. Parja had done this, he described this issue. And it's really unfortunate because there are other things like the Internet of Things and that are sort of taking its place, but there are ways to sort of take advantage of the system. And the last buzz phrase, I don't think it's a big one, is a growth and deconstruction. It's basically a way of saying that any proper database, meaning whatever you put in, you can query back out and understand what it is one-to-one with any data graph. It's isomorphic to RDF. And that means you don't have to format your data as RDF. You just describe it, especially if you're putting it through the plumbing of a pipeline. just like here's sort of the basic pieces, and that means you can join and merge things anywhere, the middle or the end of the whole analysis, and you have universal access. So there's an example from if you want to read more about this, Spivak has a book called Category Theory for Scientists, and the above thing is, of course, that looks just like a schema, which it pretty much is, though it has interesting logic composition above, which we could have done in RDF, but we can't because we didn't follow the proper rules. But the data instances, which you see a small sort of example on the bottom, if you have that and the schema, right, that's your full identity. And that's called a growth and deconstruction. It basically, the schema graph has a direct mapping to the instance graph. And RDF is sort of like that, but that makes it fundamentally possible to do that. So also just mention working together both with Biodati and Paradigm 4 on this platform. We hope to have in the next month or two real working examples, especially if we can demonstrate in front of some clients, which I have to get ready soon. And that's all I have. I'll take questions. Thank you. Mm-hmm.
What do you capture from, let's say, a BEL document? How do you translate into the format necessary to integrate it into a deep learning application? So, for example, I'm aware of approaches to statistical regression that turn a network sometimes into an adjacency matrix effectively, and then use that, in the formula for doing the regression. One thing I've always wondered when using BEL is the knowledge is fairly rich.
Mm-hmm.
Instead of adjacency relationships, a lot of information in these nodes. You have to look at causal relationships, span multiple steps,
yes.
and so on. So I'm just wondering how you bring that richness into
So we didn't deep dive one of the examples, but those graphs, they have arrows because there is directionality that doesn't have to be, but whenever you've got it, you add it. So as you said, if you've got something that says this molecule decreases the expression of that, you actually add that arrow and say that this term has a unidirectional effect on this thing, not the other way around. And if you make a decrease, you put in a bias that's negative. So that's just the simple way. Now, one of the things we used to talk forever about, how do you add other subtleties and nonlinearities to explain what goes on with real gene expression? The nice thing about a lot of deep learning is if you get the first sketch right about causality and which way it affects or its dependencies maybe on more than one factor, the other layer can deal with the nonlinearities. And that's yet to be, we haven't done this in a large setting yet, but that's the goal, is to use whatever we can just to set up a constraint and then let the learning process work with that constraint, hopefully not having to explore the completely naive full space, but a smaller space that you can do with reasonable data sets. All right, thank you.